Hi, I guess I will continue our discussion last time. I will talk more about Convex conjugate. So basically, Convex conjugate in physics, also known as the Legendre transform. And the definition is something like that. If you have a function like fx, let's say, the Convex conjugate, it can be like a vector function. X can be a vector. Um, so the convex conjugate is something like the supremum, or actually I would just write maximum because I'm kind of sloppy here. And I guess maybe people will feel a little bit comfortable to see maximum instead of supremum. So anyway, the difference is that just, um, yeah, if the space is not complete, then maybe the maximum does not exist. But here I just assume the maximum is already there. And I have maximum x lambda transpose x minus fx. I say this is basically the Convex conjugate. And and by the way, like this, of course, after taking the maximum here, you see that I'm taking maximum over x here, and afterward, like this function, I'm sorry about that, like this Convex conjugate of this fx here will be a function of lambda, right? So maybe I will call this a g lambda instead. Um, by the way, this function will be convex by itself, because like what you can see is like this is actually is a taking a maximum over a set of function, like for a set of functions of like lambda transpose x minus fx, right? For basically different x. Right, so this is a function of lambda, basically. Maybe I call it like f tilde lambda, let's say, or like g tilde lambda. And all this function, like if in terms of lambda here, it's just a fine function of lambda, right? So, and note that like if we take a maximum over a set of convex function, the resulting like function is convex as well. For example, if I have function like that, and I'm taking the maximum of everything, it will be something like this, right? And the resulting function is basically convex. And of course, a affine function is convex, so therefore, like each of these g lambda here, maybe I call it g x lambda here, like for different x, each of them will be convex, and I take the maximum of all of them, so therefore, like the resulting function, like g lambda will be convex as well. So this is the first property, like basically that's why we call it convex conjugate. Basically, you do the conjugation, the function will be always convex. So and a second property is that like this is the first property. A second property I like to mention is that like if I consider the convex conjugate and conjugate again, then I will get back to the original space, right? So after I do the conjugation, I will in the dual space, like let's say lambda here, and I do conjugate again on this f star lambda, or like this g lambda here. I'll get back to the x space there, and basically, my function like conjugate two times, like f star star x here, will be always less than equal to fx. So let's try to show that. So let's give a short proof for that. So basically, let's use the same notation here. Basically, the conjugate of fx will be g lambda, and basically f star star x here is the conjugate of like g here. So it'll be like equal to g star lambda. And so I will have let's see, wait a sec. Yeah, I will have like lambda transpose x minus fx. From here, this will be always less than equal to G lambda, right? Let's see. Yeah, that will be always true because on the left hand side here, okay, or let's consider the right hand side here. The right hand side is basically nothing but it's equal to the maximum for all the same thing for all different x, right? So therefore, if I look at a particular x here, so this of course will be less than G lambda. So then I can move the term to the other side. So I can also have lambda transpose x minus G lambda is less than equal to fx. But this is basically is for all lambda, right? So it's like for all lambda, I have this property here. So therefore, like I will have this fx here will be bigger than equal to the maximum over all lambda transpose x minus G lambda. So, but that is just the convex conjugate of G lambda of all, like this is just equal to, yeah, actually that's the, again, like this should be a function of x, yeah, if I conjugate on the conjugated function, so you get back to the x base, or like this is actually just f star x. So therefore I have f star x is always less than equal to fx. So this is the second property that I like to show here. So for the third property, so maybe I put it here, and then maybe put the both here. So the third property we want to show here is that like if my function fx is convex and is proper and closed, then f star x is just equal to fx. So but from the second property here, we know that f star x is less than fx here. So we just need to show the other way around, that f star x is also bigger than equal to fx, something like that. But the easier way to show that, by the way, I want to elaborate more. Like, I assume all of you guys know what's convex here. For both a convex set and also a convex function, basically, I assume you know that already. But a convex function is something have a shape like this is a convex function, right? And for a convex set, it's just you have a set, and you can something like that will not be convex. If I want to make it convex, then I need to kind of make it like I don't know, have all the bounds just smoothen out, got filled, basically. And we have a convex set basically, like if you pick 2 points there, if you draw a line there, like all the points between all the points on that line segment will be belongs to the set as well. And for close and proper here, I need to kind of mention the concept of epigraph. I guess maybe many of you are familiar with that already, but it will be a relation. Epigraph is just basically if you have a function, then the epigraph is the set that contain all the points about the function. For example, in the 1D space here, I have a function like that. The epigraph will be simply all the points above this function here like this. So, and if you have a 2D space, like 2D function, I have maybe a convex function like that, right? Then epigraph will be all the points about the function. So again, it's something filled inside this volume here. And you can see very easily that if your function is convex, then your epigraph will be convex. And actually the other way around as well. If your epigraph is convex, then your function will be convex as well. And I'm also like here will give us to the definition for closed and proper, like more easily using the epigraph. Basically, like a function, like convex function is closed, or like a function is closed. If the epigraph is closed, basically, you have the epigraph here, basically the set of all the points above the function is closed. So that means that like include the boundaries here. So that's just the meaning of closure here for the function. And in terms of proper, what it means is that like, okay, maybe I write it down. This is a epigraph. This means that epigraph is closed. And for proper, this means that like, it means two things. First is like epigraph is non-empty. So the epigraph can be empty if the function itself is actually degenerated somehow, like the entire function is equal to infinity. So then like you don't see the function basically. Epigraph is like there's nothing there, like every point above that is actually at infinity. So the epigraph is basically empty. And also like we want to have another property that for properness is that like it can epigraph does not contain vertical line. Hope I spell vertical incorrectly, I guess. So for example, like if it contains vertical line, it means that like for some x there, basically the function value is like is equal to minus, it's basically converged to minus infinity. And we don't allow that. Basically, we will if we say a function is proper, then like we cannot have function something like basically an example is a affine function, for example. In that case, this will not be proper because for some actually I'm not sure. Yeah, this probably not. Yeah, I'm not sure this is a, but maybe maybe I have yeah, just maybe a better example, any example, and maybe I can have a function like tangent or something that will goes to infinity, then like apparently it won't be proper because like that function can go to infinity. So anyway, so again, like what we just say about these properties that like if we have the epigraph, the function is convex, proper, and closed, and like the convex conjugate of the original function is equal to itself. And so how to prove this? So it's the easiest also to look into the epigraph itself. So we basically have, maybe I just draw it in 1D. So I have like function fx from the second property here. I know that fx is above f star star x, right? So I have something like that. Like this is f star star x here. So yeah, this is supposed to be convex, but yeah, my drawing is not very great. So now if this is basically if fx is equal to f star star x, then we should have the epigraph of both of these functions is basically the same. So if not, then you have the epigraph is basically is above. So basically I have the epigraph fx here is above like this the surface of this function here in f star star x. So then we basically, if that is the case, we must have at some point, like let's say I pick a point here, maybe I call it like x tilde such that like this point will be can be separated from the epigraph of fx by some plane here, some plane in the basically R n plus 1 space. So I assume that x in the n space, Rn. And of course, the epigraph, by the way, lies in the n plus 1, Rn plus 1 space because besides the x here, I also have fx for the extra dimension there. Now, so I can separate that, meaning that like there should exist like some, maybe I call it lambda here, such that like lambda transpose, okay, let's say like I have a point, say like this point here is like, okay, let's write this point here, say this point here is basically x tilde and f star star x tilde, right? And for any point on inside the epigraph, or like some point like there will be like x, maybe on the function of fx here will be f, let's say some fx, fx here. Now I basically I should be able to separate these two function here. So another separate these 2 points here, like this point with this point here. So therefore, like I should be able to find a projection that's a normal vector. Let's say the normal vector can be like lambda and w, such that like this guy, let's see, is yeah, is less than this one. And I may even put an epsilon here because this is strictly like lower than that, like epsilon for some finite epsilon here. I should have like this thing plus epsilon is less than equal to this guy here. And I'm also like, because I can normalize like this W and lambda here, I can divide everything by the lambda here, W here. So let's say instead I have like lambda W and epsilon here, I can divide everything by lambda. I have lambda over W, then this become 1. And this is lambda over W and 1, and this epsilon for W. And of course, I can rename this lambda over W as lambda and epsilon over W as epsilon. Also, like, then I just get back to that. So with this one here, what do we have is actually we have like lambda. Maybe I should. I'm a little bit sloppy here. They probably have a transpose somewhere here. Yeah. So I have like lambda transpose x. X transpose lambda is equal to lambda transpose x. So let me put lambda transpose x here. Minus, yeah, I can put even -1 here. I can divide by minus W instead of like W. So I have -1 here. So I can have like this one plus epsilon is less than x tilde lambda transpose x tilde minus f star star x tilde. Yeah, something like that. Now note that like this is true for every x, right? Because on the entire function here, like this plane here should separate this point like x tilde fx from all the points like on the boundary of the epigraph. So therefore, like this is true for all x. So therefore, I can do this a maximum of that or like supremum of that over all x. And this will definitely give us So even though I have infinite number of functions here, but because I have a finite epsilon here, so this guy will be always less than equal to yeah, actually, maybe I can go straight to that. So I can always argue, so therefore the f star star x tilde is bigger than equal to the maximum x lambda x minus fx. Yeah, because this is true for all x, and I have this is epsilon here just as buffer, just ensure that this like straight inequality still hold. Now then, like this guy here is nothing, but it's actually equal to f star, or maybe I use g here, g lambda, right? It's the conjugate of that, g lambda. Well, I can pull this g lambda on the other side. So I will have actually f star star x tilde is less than lambda t x tilde minus g lambda. But note that this is actually a contradiction of the definition of s star star x tilde, because this is actually the conjugate of g lambda, right? I'm trying to do conjugate of that to get this, right? So, but the conjugate of that is actually this guy. So this guy therefore supposed to be equal to the supremum or maximum of lambda tilde x minus g lambda here. So that gives us a contradiction. So therefore, like we must have the original assumption that like there's some point on f star star x on the boundary of the epigraph of f star star x can be separated from the epigraph of fx is not possible. So okay, I guess I was next. Yes, I guess okay. I will. Let me start a new page here. So I will just briefly mention the kind of the connection of Convex conjugate with Legendre transform. Of course, it depends on like the definition where you see the definition. Some definitions precisely where the Legendre transform is exactly equal to Convex conjugate. But I first came across that like taking a class on thermodynamics, and the Legendre transform is like simply put it as just actually I maybe let me write the I guess I can just erase this here. So I'm going to basically recall some of the stuff we mentioned last time. We have the consider in thermodynamics. So we have internal energy of maybe an ideal gas system. So we have U, and as a function of S and V. So this is an internal energy. So by the way, this is thermodynamic of like let's say ideal gas, right? And this is the entropy, and this is the volume. And by the way, the total derivative of U can be written as a T ds minus P dV, where T here is the temperature and P is the pressure. So meaning that like basically you can think of S and V as independent variables. So they can be independently changed. So and so immediately you see that like so therefore if I take a partial derivative of U with respect to S should be equal to T, right? So and And basically, the Legendre transform in thermodynamics is we trying to instead of like taking S as the independent variable, let's say S and V as independent variable. Let's say we want to take like T and V as independent variables, especially the entropy is hard to quantify. So it's much more convenient to quantify and measure. It's much easier to use T as independent variable. So to do that, you see that if I simply consider U minus Ts, what we have is if take the total derivative of this expression here, so we just give us a du is this equal tds minus pdv, and then ts is a tds minus sdt. So like I have these two got cancelled. So now you see that this expression is actually a total derivative of this expression, which depends on like basically v and t instead. Now v and t is like the independent variables, and this things is known as the free energy of Helmholtz free energy that we mentioned last time. And by the way, like how do we see this is actually just the Convex conjugate? Because if you think of the Convex conjugate here, so if we have the U and we want to do a Convex conjugate on the variable S here, then we can have like S times some lambda here, let's say, take the maximum over S minus U, right? And now for this guy here, maybe I just call it U star. So the Convex conjugate for that. For the Convex conjugate, so for this thing, like when we take try to define the maximum, like we can simply take the derivative for S here. So we have like the derivative of this guy, we just get lambda. So this is like partial U partial S is equal to 0, right? So this give us a lambda is basically equal to partial U partial S. And partial U partial S, by the way, is just equal to T, right? So then we see that actually this will just give us back like equal to Ts minus U. So therefore the Convex conjugate of U here is actually just equal to the minus of this free energy. So indeed it's a Legendre transform, or even though there's a sign like change here, but basically the Legendre transform in this is just the Convex conjugate. So I guess like finally I just want to do one more example, also an example that we did last time. Let's see. Let's just start a new page here. So let's consider the improbability. Like we have like energy based model. We have let's say Px by Boltzmann distribution is equal to some E minus beta Ex, and like this is a normalized over like Ex like dx, let's say. So in the sense that E is the energy of the state X here. So if the energy is higher, the probability is lower, so that we have exponential minus. I have the minus here. And beta is like just the inverse temperature. So beta is equal to 1 over T actually. And this, of course, like this is just a normalization factor. Like this is known as the partition functions in physics. And usually use Z to represent that. And we can consider the log-partition function, like maybe I call it A here. The log-partition function, by the way, is convex because you can, I'm also like have a nice, interesting cumulative generating property. Actually, we mentioned that last time. You can easily verify that, like if I take partial derivative of A with respect to beta, it will give us like the expectation of Ex. I think there's a minus sign here. So this is so therefore it's actually equal to the minus the internal energy. And if I take the partial derivative of beta again to trace, this actually will give us the variance of Ex. And of course this is bigger than equal to 0, so therefore like with respect to beta, A is a convex function. Now if A is a convex function, we can again try to find the convex conjugate for A, and the convex conjugate for A, by the way, will be, yeah, let's do that like as an example. So A, of course, here is actually a function of beta, right? So it's a function of beta here. Like C is a function of beta. Yeah, I should put it more clearly. This guy is Z, and A is equal to log C. So the convex conjugate, let's say A star. So let's use again like maybe lambda as the parameter is equal to A beta. Let's maximize over all lambda minus I should say lambda beta first minus A beta, something like that. Then find the maximum. Again, we can take the derivative with respect to, sorry, this would be like maximize over beta. The derivative with respect to beta. So I will get lambda minus partial A partial beta is equal to 0, right? I want that derivative equal to 0. And we already mentioned that this one, but yeah, you can do a try to compute yourself, or like you can go back to the previous video, like we have shown this. So partial beta is just equal to the minus expectation of the energy, or the internal energy. So therefore like lambda will be just equal to partial A partial beta is equal to the minus internal energy minus U, something like that. So therefore like the convex conjugate, by the way, is just equal to minus U beta minus A beta, something like that. And of course beta now is actually a function of lambda here. Wait a sec. Yeah, lambda is of course is just U here. I don't know how to. It's okay. Let me just write like that. So this is beta actually a function of U here. Because lambda in any case is just equal to minus U. So beta is a function of lambda. So therefore it's a function of U. So I have A beta is a function of U, something like that. Or you can think of it just, yeah, A beta. It is okay. So yeah, we have A star is like that. By the way, we can go further. Like, what was the physical meaning of like A star here? So it turns out that A star here says nothing, but it's just the entropy. Because like if you think of like what's the entropy maybe let's use S instead of H here, like because we study kind of physics here. So S is equal to expectation log, let me minus expectation log Px here, right? So therefore like I have Px, I have beta Exa, I have expectation beta Ex, I have minus pi, I have plus again expectation log log C, yeah. And of course log C here is just equal to A, right? So therefore I really have a actually I have yeah, okay, that's fine. I have this is equal to beta, put it out. So expectation E is just the internal energy, say. So this is entropy is equal to that. So this is actually just equal to minus entropy. Yeah, I think I have a sign error here. I mentioned that it's equal to the entropy, but it should be like minus entropy. But anyway, like yeah, I guess that's it. Like that's more or less I want to talk about. So thank you for attention.